We're now going to just look at a bunch of disciplines, still within our physics realm. If we're looking at the current in a wire, that exists whenever you have electrical charges that move. So if we're looking at this picture, looking to see the average current here would be if we look between 2 points and we computed the difference in the charge over the difference in the time. If we let the time go to 0, did the limit as delta t approaches 0, we have the derivative of charge, and that is current. So current is the rate of change which the charge flows through a surface. We have power, and power is the derivative with respect to time of work. So just giving some examples where rates of change show up in the different disciplines. In chemistry, if you have the concentration of reactant A, and we have the number of molecules per liter, so it's denoted by this bracketed A, and the concentration varies during a reaction. So if we're looking at this concentration of the reactant per liter for A, B, and C, they're all functions of time. And the average rate of reaction we have here, see we have the differences here and the difference between time. If we take the limit as this delta t approaches 0, then we have the derivative with respect to time. In thermodynamics, we can look at the rate of change of volume with respect to P, which would be pressure, and as the pressure increases, the volume decreases. So here this shows the derivative being less than 0. We also have what's called isothermal compressibility, and it has to then do with this derivative, and then it's this inverse relationship, so inversely proportional to the volume. So the idea is here not to remember all of these equations or even necessarily write them down, but to just see how the derivative, the rate of change, shows up in many things. In biology, if you're looking at the number of individuals in a plant or an animal population, you would have an average growth rate, but as we let our delta t approach 0, we have the derivative. So the derivative gives us the instantaneous rate of change. Now, if this was the number of animals, it would be discrete, so it would really look like these blue things here, but it would you could model this with a continuous function, even though our animal population changes by 2 animals, then 3 animals, not 2.3 animals, but it can be modeled with this continuous function. If we look at the flow of blood through a blood vessel, such as a vein or an artery, we can model the shape of the blood vessel with a cylindrical tube that has radius capital R and has a certain length L, and the relationship between the flow of blood through this vessel and R is given by what they call the Law of Laminar. And this Law of Laminar, here's the equation, but again, like I said, we don't need to have all of the details here, but we have the viscosity of the blood and the pressure, and if the pressure and the length are constant, then the velocity is a function of this little r. And so the rate of change of velocity as you move, little r is the radius of this, where you are located between 0 and big R. And so if we look at that difference there, depending on how the velocity changes as we move positions out, it's called the velocity gradient, and it is the derivative. So dv dr, which means the rate of change of velocity with the rate of change of your radius. So rates of change occur everywhere. A geologist may be interested in the rate at which molten rock cools by conduction of heat into surrounding rocks. An engineer, rate of change of water flow into or out of a reservoir. An urban geographer, rate of change of population density in a city as the distance from the city center increases. Meteorologist, the rate of change of the atmospheric pressure with respect to height. All of these things have one single mathematical concept: the derivative. The derivative is the rate of change, comparing 2 variables at an instant. Very often it's the rate of change with respect to time, but it doesn't need to be time. So this just gives another list of various things that would have rate of change. The derivative. Then just one last quote. The French mathematician Fourier said, "Mathematics compares the most diverse phenomena and discovers the secret analogies that unite them. And the thing that unites all of these things is the derivative."